In this example, we're going through a static equilibrium problem. And the setup is pretty simple. We've got a beam that is 100, it's 3 meters long, and it's 100 kilograms. So 3.0 meters in dimension, 100 kilograms in mass. And the idea is that there's a, I guess I shouldn't have wrote it on right there, but sorry. There's two supports right there, okay? And so obviously if it's 100 kilograms, 100 kilograms, 1 kilogram is 2.2 pounds, so it's 220 pounds. So you would expect that a scale on either side of the beam would read 110. It would read exactly half of the total weight of the scale. And so that's clear. You don't really even need to introduce torque to know that. But what happens when there's an asymmetric load? So what I'm going to do is I'm going to put a person right here. Right, let's, oh, they should probably have a head. 80 kilograms. That's the person. Drawing is not that good. And they're 2 meters from the left edge. So the question is, how does that affect the weight of the scales on either sides? This is a problem that you cannot do with just forces. There's no way to solve it with just forces. You have to use torques. Sometimes we call them moments. Let's draw a rigid body diagram. A rigid body diagram, unlike a free body diagram, the location of the force matters. And so what are all the forces acting on this beam? Well, it's a 100 kilogram block. We got gravity pointing straight down. So that's 100 kilograms times 9.8, so that's 980 newtons. You also have the normal force of the person, right? The person's push, I mean, it's not the gravity of the person, technically. It's the force of the person on the beam. It just happens to equal the same as the Earth's pull on the person. So that's at 2 meters then. So 80 kilograms times 9.8 is 784 newtons. Just multiples of 9.8 that I have memorized. And then finally, you have the left and the right forces that are asymmetric. They're not equal now. So relatively smaller, F sub L, bigger, F sub R, lowercase l, lowercase r. Right, and so adding these forces together, we've got, work in a typical coordinate system, X and Y. Where's the origin of the coordinate system? Well, that will depend on where we choose the axis, which I'll talk about in a second. So summing the forces here, we've got plus FL plus FR minus the sum of those forces, which is 1764. That equals 0. So again, just by summing the forces alone, we know that the two asymmetric forces have to add 1764, but it doesn't give us the actual values. It's an underdetermined system. So we need another equation. That's where torque comes in. So when it comes to torque, what is the torque? Well, you have to be aware that what you mean when you say calculate the torque. Because sometimes people think, well, how is there a torque? It's not even moving. That's the same thing as saying that how can there be forces acting on you if you're not moving? Right? You drive in a car, there's all these forces acting on you, and yet, well, you're moving, but not moving in the car, but you're sitting on the couch or whatever. Forces are still acting on you, friction, gravity. Same thing here. There's torques being acted on the bar, and yet the bar isn't moving. But where is the axis? If it's not rotating, where's the axis? And that's where we're free to choose. It's going to turn out that no matter what axis you choose, you'll always get the right answer. So you choose the one that's easiest. So let's select the left edge. And so in the coordinate system here, maybe if I draw this a little more abstractly, at 1.5 meters, we've got 984. So that's a 984 or 980 Newton force. And at 2 meters, we got the 784 Newton force. At the origin, we have our unknown, FL. And at 3 meters and 0, we've got FR. Right, so calculating the torque around this origin right here is pretty straightforward. Now, because we've got our moment, we have our moment arm for each of the vectors. And so the first one is, well, the first one's going to create a negative torque, the 980 force, because again, on its own, around the left edge, right, that 980 Newton force would make the thing rotate, clockwise. So it exerts a negative torque. So when we sum that up, it'll be minus 980 newtons times 1.5 meters. Similarly, the 784 newtons times 2 meters. And then F sub r, although it exerts a positive torque, we don't know what it is. I mean, we kind of do, but that's going to be plus the unknown torque, which is 3 meters times FR. That all equals 0. And so you see that we have the torque equation that will give us one of our unknowns. If you would have chosen, say, the right edge, all these coordinates would have been different, but you still would have gotten the answer for the left force. And so 980 times 1.5 is minus 1470. Newton meters, remember the units are still Newton meters. 784 times 2 is 1568. Newton meters, that equals minus 3F. Add those two together. That's just like 1500 plus 1500 minus 30. That's pretty much what it is. So we get 3038 Newton meters equals 3F, from which we get that F sub R equals 1013 newtons. And then since we know F sub R, then F sub L equals 1764 minus 1013 newtons. And so we get that F sub L then equals 751 newtons. At 150 pounds, and the other one is about a little over 200 pounds, which makes sense because we are at 100 kilograms plus 80 kilograms is 180 kilograms, which is almost 300 pounds. So yeah, that's about right. Had we tried it with the right axis, we would have solved for F first in the torque equation and would have been able to solve for FR from the force equation. Or choosing any other axis, we would have gotten another simultaneous system of equations. Maybe in the middle, it would have been, F1, we would have gotten like pluses and minuses. We have to, solve somehow, but you always get the same answer because torque is always 0 everywhere, no matter what axis you choose. Remember, torque can be this thing can rotate around any axis. There's infinitely many axes to choose from, and these specific forces at their relative locations all give zero combined torque at every axis. That's what it means for static equilibrium.